thanks everyone for attending, and I hope you had a great time so far in the at Spring Days. How many of you have I'm sorry, I missed the show of hands. How many of you are even try to take a look at Spring Cloud Data Flow, Spring Cloud Stream, that ecosystem of projects? One hand, two hands. Okay, so by the time we end this presentation, I want when we talk a little bit later in the open space, I'll ask the same question. I hope I get more hands showing up. So my name is MARIUS BOGOEVICI. I'm a software engineer with Pivotal. I'm a contributor to the Spring Cloud Data Flow ecosystem, and in particular, Spring Cloud Stream. I've been a Spring contributor since 2008, so I've kind of been in this enterprise integration, data streaming space with Spring for quite a while. And as you'll see, the projects that we're talking today kind of leverage that the very, very deep history of the Spring framework in terms of messaging support and integration. So without belaboring the point, it's a long title, right, if you notice. And I'd like to just go through a few concepts before we actually move into the heart of the matter, which is the introduction to stream and data flow. How many of you have using are or feel like they're developing applications that have a streaming use case right now? So what's your, how would you define streaming use case?
How would I define streaming? I guess I would just say a stream is a collection of events.
OK. OK, so collection of events in order. So that's a good point. And I think it kind of captures what, in a way, what I'm trying to say here as well, which is essentially that when we look at streaming, we think about processing large quantities of data as fast as possible in real time. There are different use cases that drive to this point, ranging from real-time ETL, really change data capture that's kind of ingesting data into an analytics database, and you don't want to do that in batch. You want to have that data available as soon as possible, ranging to things like predictive maintenance, fraud detection, where you actually want to capture events in real time, and you want to detect different situations that occur before they actually occur. And we've arrived there to a number of paths, and one of them is essentially the desire to reduce the latency of what's been traditionally done through batch processing. The other one is essentially by trying to capture and trying to transform these use cases that initially kind of were relying on sporadic events to kind of monitoring a more finer grade evolution of a system over time. It's the case for predictive maintenance, for example. In a classic enterprise integration use case, you basically get a message when the car has broken, right? With predictive maintenance, with the ability of actually kind of streaming more data, getting more data from the system, you actually don't do that. You monitor the state of the system, and you try to infer different conclusions about how the system works. And very good point from Stephen, actually, they're correlated events. So one of the big differentiators in streaming is the correlation between these events, is that I don't deal with sporadic data. I'm actually interested in the order in which they arrive. I'm actually interested in the way they're grouped together. I'm actually interested in processing, for example, data that's coming from the same sensor, right? And that has led to other to requirements like operations like grouping, ordering, windowing that we want to provide, we want to perform on these data streams. It also has led to rethinking the middleware design, ranging from essentially, when you think of messaging, for example, you have the traditional model like JMS, RabbitMQ, but then for the streaming use cases, you see some more things going more in the direction of using log-style messaging systems like Kafka, for example. Kinesis is another one that follows that pattern, or Azure Event Hubs. You see a desire to actually move data and kind of provide a large-scale cloud-based environment for processing that data for cloud-based messaging systems such as Google PubSub and Amazon SQS. In particular, we talk about messaging and why we're looking at this. And we'll talk about messaging microservices. What's our interest in microservices here? Again, microservices are a very, very belabored point. So you get all the, like, it's probably like a very, it's a topic for a presentation in and by itself. The interest here is basically in the kind of advantages that microservices provide in terms of cohesiveness, organizational alignment, development agility. So you get all these things that they enable you to write software faster, right? And again, when you're actually writing data processing applications, you want to be able to experiment, you want to introduce new processing strategies into the system, right? So obviously there are like also technical reasons, like failure isolation, and very importantly, especially again for data processing, is the ability of tune resources in a very granular way. Certain parts of the pipeline, for example, require more memory if you do data enrichment. Some other parts of the pipeline require more CPU, right? A monolithic structure, something that's you have very little control over how these different parts of the pipeline evolve, obviously are much harder to tune. Network in particular is a big issue because you can give an application a lot of memory, you can give it a lot of CPU, but you cannot, like usually network is a bottleneck in situations like these. You cannot just go beyond what the network interface gives you. So sometimes if you have like a really, really high throughput, you actually have to scale up over multiple nodes. It's something to think about. Now, in particular, we're looking at event-driven microservices as a paradigm of choice. So communicating through a broker as opposed to HTTP, as opposed to point-to-point communication, gives you some advantages in terms of reducing the communication complexity. Applications are decoupled, don't have to know what the other destination is. It's like I don't just send a message to a specific topic, to a specific destination, and I can have one or more recipients of that message. Other applications can actually become part of a more complex graph. So the adoption of this communication model between applications has benefits in our opinion. It also solves problems like for example, how do you do distributed transactions? How you ensure data consistency between the different parts of the pipeline? Again, that's another like very, very big topic for discussion. Just want to frame the conversation saying that what we see here, and this is like one of the biggest, like one of the ideas driving this discussion and what we do is that at the end of the day, data and event streaming, so let's say big data type of scenarios like analytics and ingestion and that kind of stuff that's usually kind of seen as separate from, let's say, the business messaging scenarios, which are closer to evolved enterprise application integration, things like event sourcing, for example. While they're, let's say, different use cases, they're conceptually very, very similar, right? So part of the design of what we do is kind of inspired by this thought. The other problem that has to be solved in this context is operational complexity. So we're very happy that we've made a good argument for using messaging microservices, and now we have to build and run them. And that's not an easy problem to solve, right? Distributed systems, which is what we describe, are inherently complex, but then if you try to operate them, you have even more work to do. So operating this like fleet of like very complex system actually comes with some prerequisites. You don't only have to, like you're saying, well, if you have microservices, you can scale them up easily. Fine. Where do you get a machine from? Where do you get a new, like where are you going to run this new instance? So you have to have this ability to self-service and provision new instances of your application. You have to be able to monitor these applications. So you just start 3 or 4 applications on your machine and start trying to figure out what they do, and it's already very complex. Like you have to, like you can't just manually go and check the state of each and every one of these applications, right? What if they crash? What happens? Who restarts them? Who monitors them? Who manages that, right? You have to figure out how to, like we say, well, it's easy to upgrade a version, like it's easy to upgrade a part of your pipeline by just deploying a new version. Perfect. Who's going to build and run and test that version and make sure that it makes all its way to production, right? So those parts are actually critical in this context, right? And those are also the parts that we actually don't care too much about doing them ourselves. That's the part that's, while exciting as it is, we want it to be as boring as possible. That's not where we add value by monitoring these two things. We add value by writing our applications and designing structure. So in that context, that's the cloud native aspect of what we are looking at. We want our microservice fleet to target a platform that basically takes care of all these aspects like resource management, scaling, monitoring and failover, routing load balancing, right? Even rolling upgrades. And if you see a few of these platforms, actually incidentally they're the platforms that are supported by Spring Cloud Dataflow right now. What we want is to provide a way to write applications easily and to provide a way to actually deploy complex graph of these applications on these target platforms. So the use of a platform with these capabilities is kind of core to our view on how to read and write your data pipeline, right? And again, it depends on the capabilities of the system. You have a full-fledged PaaS like Cloud Foundry, right? Which basically operates at the application level. Or you have like something like Kubernetes. Or you have something like Mesos and coming up down to Yarn, for example, as which has probably the least set of capabilities in the sense that it doesn't necessarily do monitoring and failover elastic scaling, but it's still a resource manager. The point is, you don't want to do any of these things yourself. You want to delegate them to a platform. And this thing has been coming like this. We have arrived to this conclusion through our own experience. How many of you have heard of Spring XD? More hands than Dataflow. So Spring XD basically was the first incarnation of what we do right now with Dataflow. We started writing our own cluster. We started doing our own cluster management and like managing deployment of applications. And we were very happy up to the point where around 2015 we figured out, OK, Spring Boot and Spring Cloud are very mature right now. Rather than building and managing our own stuff, we can actually kind of rely on the support that Spring Boot in particular and Spring Cloud provide for writing microservice applications. And we can just take care of managing them. And this is basically how the projects like Spring Cloud Stream, Spring Cloud Task, Spring Cloud Dataflow have been born. Right? And I'm going to talk today about Spring Cloud Stream and Spring Cloud Dataflow. I just wanted to give you a perspective of where our thinking came from and what was the motivation for us going through all this effort. Essentially, what we want to end up with are messaging applications talking over, like microservice applications talking over messaging middleware and running on one of these platforms. And that's what we're going to build in the next minutes. First, the building block for our streaming applications is Spring Cloud Stream, which is essentially a framework that aims to simplify the developing of messaging applications. It takes care of abstracting out the messaging middleware, like treating it really like a commodity. You don't program, like your programming model is not biased towards a specific messaging middleware such as Rabbit or Kafka. You just think in terms of, I receive a message and I have to process it, and then you delegate to the framework the work of actually connecting it to that. It's built on, it's built basically on components that have a very deep history, like Spring Boot, in particular Spring Integration. How many of you are familiar with Spring Integration? Right. So you can think of, you can understand a lot of the stuff that happens in Spring Cloud Stream just by thinking OK, automatic provisioning of channel adapters, for instance. It goes a little bit beyond Spring Integration, but that's a good place to start. It's a lot of use cases. So the assumption there is that every application consists of a application core, which has, like as I said, a very abstract programming model, and then it declares a number of inputs and outputs. And the inputs and outputs are automatically managed by the framework. These inputs and outputs can be typically message channels, if you're familiar with a message channel for Spring messaging or Spring integration. But we support, like recently we started looking at other things, such as reactor fluxes and Kafka streams. So it's a very extensible model in a way. The idea is that with the uniformity that these components give you, you can actually start building like wonderful things here, right? And the core of the heart of the entire framework is what we call the binder. So these, the channels that you have declared in your application will be created by the framework, and then the binder essentially takes care of connecting them to the message middleware of your choice. Also, the whole process is using Spring Boot properties, which means that you can alter and manage the characteristics of these channels or inputs and outputs at like when you deploy your application. So it supports the entire breadth of options that Spring Boot gives you. What does that mean? It means that, for example, you can change the target destination of an application from, like, you don't have to hard code it in there. You can actually choose it when you launch it. What Kafka topic, for example, does it consume from, or does it write to? And actually, that's quite an important thing with when you get to Spring Cloud Data Flow. In terms of programming model, it's very simple. You have the annotation, you add the binary implementation on the class path. We have 2 production-ready implementations, which are Kafka and RabbitMQ. And we're currently experimenting with Amazon Kinesis, with GMS, and with Google PubSub as well. So there is a variety of things that you can actually kind of try out for your deployment. The idea being that your application model remains pretty much the same, right? So this is essentially a tweetable, very simple application that does an uppercase transformation. So it's very simple. It's basically saying that from the abstract, it consumes messages from the abstract input named input, and it sends data to the abstract output named output. The thing here is that this application, it's what you notice, and this is basically where it becomes interesting in the context of streaming, is that this programming model is supported, is classic, you can recognize it, it's something that we do when we do messaging. But at the same time, it's very biased towards one-by-one message processing, right? It's not very contextual. I cannot derive any context of like a larger context of events in which these messages are processed. This is where I'm saying that we're actually supporting as a programming model, not necessarily in terms of, like we support it both as, like we are biased towards a more functional programming model based on Reactor. And we support it in 2 ways. Through adaptation over existing messaging middleware integration, which means that the system is not necessarily reactive, but the programming model is still functional. We also have an integration with reactive streams that allows us for the programming model to, or for the entire application to be reactive. However, if you notice this example, it's very similar to the first, but it uses the reactor flux type as an input. So the framework takes care basically of converting the input of the application in the flux of messages. And how many of you are familiar with reactor and flux? Victor. Well, you have been in Victor's talk yesterday, and then you should. Anyway, what that gives us is basically, if you see this, like if you look at this example, it's not very spectacular. So I'm converting, like I had the one-by-one message conversion on one hand, I have one-by-one message conversion on the other hand. What's the big deal, right? It becomes a big deal when you look at operations like grouping and windowing. And you start looking at these types of transformations in like you can actually take a more holistic view of the entire of the entire stream of data. You're not processing messages one by one. You're actually describing how the entire flow is transformed, right? In this case, we're grouping messages, we're counting them, and then we're sending the result out, right? So that's that's a big motivation for supporting like a reactive programming model, and a functional programming model is an alternative to the classic enterprise integration and classic messaging style, imperative, one by one, right, model. The model itself is based on pipes, like it really has a pipes and filters structure. So the idea is that every application is isolated, consumes data from a destination, sends data from a destination. It's very unidirectional in a way. So this is where I'm saying that we're very opinionated about how we do things. And one of the assumptions that we make, and this is one of the opinionated primitives, is that all the destinations that we communicate to are publish, subscribe. And not only publish, subscribe simply, but durable publish, subscribe. So we will configure, like when Spring Cloud Stream basically kind of interacts with a messaging system, it provisions the infrastructure over which these two applications communicate. For example, in Rabbit, it uses an exchange, and it configures consumers so that there's some retention of that data. In Kafka, which has been kind of a big inspiration for us, this kind of thing is done automatically, right? In Kinesis, again, we use streams and shards. In any case, the model, as I say, is that we have like these destinations to which the applications communicate, and these destinations are provided as configuration options to the application, right? And they're kind of abstracted out from the input and output names. With all the destinations being published, subscribed, comes the problem of competing consumers. So it's great that I can have two separate applications and both of them receive like the same message, and that's fantastic because now I can branch out and I can build very complex graphs. But what happens if I add more instances? Obviously, if I add one instance of each of my application, I don't want them to consume the same data, right? So this is where we borrow the concept of consumer groups from Kafka, and we're applying to other messaging systems as well. So there is like a high-level configuration option that you can tell, look, you as an application, when you consume data from this input and output, you're part of this consumer group. Therefore, you will be in a competing consumer relationship with everyone else in that group. Between groups, the relation is still publish, subscribe. So different groups of logical applications will receive the same messages. The other problem that we have thought about, like as a high-level primitive, is partitioning. So, especially when you do stateful processing, the fact that you have competing consumers is not enough. Imagine that we do average calculation, or we calculate the average value of a sensor over time, right? Data from different sensors may land in different instances. And all of a sudden, I have two averages from two different nodes, which don't make any sense. So we've taken the particular step of again, lifting partitioning as a high-level primitive and providing each output destination with the ability of specifying a partitioning strategy for the data. So whenever an application writes data, it can be told, look, you have to partition data this way. And again, some messaging systems have like native support for that. In some other systems, we actually take the extra step of configuring the queues and for example, the routing keys for those in Rabbit to take care of this. But you as an application only need to know that you have to specify a property that tells how that output data needs to be partitioned, right? So let me go real quick and show you exactly how this works. And I'll make sure that, so I'm going to start Kafka real quick. here, and okay, so I'm going to create very quickly two applications, one that sends data, one that receives data. And I'm going to use Spring Initializer. So it's as easy as this. I'm going to create an application that receives data from HTTP and writes it to, sorry, it's not a valid thing. Receives data from HTTP and writes it to an outside topic. So I'm just going to say stream Kafka as a dependency. And I'm going to say web. And that's it. And this is going to create a source. Let me just change the size of the font. So this is a very basic application. How many of you are using Spring Initializer currently, right? This is a very simple way to, definitely encourage you to use that, especially if you're getting in Spring Boot. And as you see, there are only two dependencies basically generated by Spring Initializer, the Kafka binder and the web start. So what I'm going to do next, and well, as much as I'd love to live code this through the entire demo, I'm just going to do a copy paste, which probably no one should do, but it's okay for demos. Just in the interest of time. And I'm creating this very simple HTTP, as I say, and it's an HTTP endpoint that sends data to the outside world. And this application basically has a controller method. Like you see, it's a controller. It has a, it's a regular It's good that it happened to you, not me. Like that would have been very, very tough to handle. So it's a regular controller method, and you can see this source object here. And the source is like one of the predefined interfaces. You can of Spring Cloud Stream. You can define your own interface with a number of input and output channels. But what you can see here is that we have a channel named output, and this has the logical name, let's say output, that we're going to use for the app. So with my application, I can just say, look, I'm connecting here. I'm whatever data I receive, I just send it out to a specific destination. And this application actually has a, let's see, okay. So let me just, so I can configure, for example, the output destination. And I'm going to call this words, and you'll see immediately why. And that's pretty much it. Like, I can start it. So you can see it creates, like, the application creates a topic named words. It's very, very small. I'm sorry, I cannot make this larger, and I don't know how to, anyway, to zoom into, but you have to trust me. There's a topic named words over which the source application sends its data. And now I'm going to create another module, which is going to be a sink. It's actually the application that receives the data. And I'm going to create the sink. And this application is actually quite a simple one. I'm just going to add the enable binding annotation, and I'm going to tell it, like, look, it's listening. It defines something called a sink. A sink is another predefined interface that we use. It has one input channel, and it's used for, actually we're going to use it for receiving data. And I'm going to data, and I'm going to say public void log. Right. So I'm going to say system outs. I'm going to just send the data that I received. And the other thing that I have to specify is, okay, I'm going to connect this application to the words destination that the other application writes to. So I'm going to start it. Again, it starts, it connects. Oh, sorry. Because they are running on the same machine, I actually have to give it a different port because it also has a web endpoint for exposing actuator information. So it started, it listens to the ports. And so now I can just call some data into this application, right? And I really apologize for you can see in a very small font at the bottom basically the message being displayed and being received by the other application. And I can post it again and again and again, and basically I get all this data in there. So in a very simple way, I've built two applications that talk to each other, communicate over Kafka, exchange information, and do that kind of stuff, right? And I can create even more complex things. So kind of going for a canned example, I have the word count application that I showed you on the slides, which does, let's say, which counts the words, like basically breaks down the lines received by the application and counts them and exposes them as and basically writes out the count for within each sliding window. And what you see here interesting is that this application basically returns a POJO, returns word count, right? So what we can do and what we did here is that we use a setting, for example, that also string called stream provides to specify how the message should be output. So in this case, we want to write this, like we want to automatically convert this output to JSON, right? Which is the way we actually want to in that way, we actually make the data portable. So another application can receive it, and I don't have time to go to the full demo, but you will see other, like if you go on the site, you will see other demos where the data produced by this application can be basically parsed and received into an arbitrary object that maps to that JSON. So we have this portability of data between two applications that doesn't require you to share types. So starting this application real quick, I'm actually going to insert this into the pipeline. And so I'm going to redirect the log application right now to the, I'm going to say the destination is counts, and this one writes to words. I'm going to start both again. And you will see actually the three applications talking to each other, right? And what I'm expecting is just anytime you rehearse something, it leaves garbage on your system. So this is why you actually need better management for your applications, because you don't know exactly what runs and what doesn't, which is exactly my case here. Anyway, let me get back to the... So restarting the original two apps. Now, in the word count application, actually what I'm going to receive when I start sending data. Okay, I think I have a bug in the word count application, which basically normally I would expect this to display the total count, but obviously it doesn't. It just displays one. So that's one of the things that happens with demos. In any case, apart from the fact that the logic in the word count application doesn't work correctly, which is my fault, you can see the 3 applications being pipelined and connected to each other and communicating, and you can see the message conversion taking place, which is, I think, what was the main point that what I was trying to get. So that is basically that. That is essentially how, like, you can see this, like, you can see the aspect of, okay, I can easily write applications, I can easily connect them to each other, I can easily configure them using Spring Boot, right? But there is a problem of complexity here. And the problem is that while simple applications are very easy to deploy, what if it's already, you see already that it is pretty complex to actually deal with 3 applications, right? What if I have more? What if I have more instances? What if I have more? What I have to configure all these things? Like even this is probably not one of the most complex things that you can do, and it's actually quite dreadful for me to do it right now, right? So we have to think at a bigger level, right? We have to think of these things as like managing complex application graphs and deploying them as a higher level concern. And this is where Spring Cloud Dataflow comes in. Spring Cloud Dataflow provides a DSL for deploying stream topologies, provides a REST API, provides a shell. So essentially breaks down the 2 problems, describing complex data structures and deploying them on different platforms. In terms of a DSL, it has this like very Unix-like specification. What I wrote there, like the HTTP application, writing to word count, winding to log, and so on and so forth, really becomes more like a Unix-like pipeline description. It deploys on various platforms, right? So once you have the specification, it's broken down, it identifies the artifacts that match those descriptors. When you say something like HTTP, it knows that HTTP actually is a jar that sits somewhere in Maven, or it's a Docker image or something like that, and it knows how to deploy it, right? And it deploys that using an SPI. So it's basically, it's pluggable. Like the same strategy, you can have the same descriptors, the same DSL applying to different target platforms, like Mesos in this case, or Cloud Foundry, or Kubernetes, or Yarn, right? So our application right now is kind of coming, basically that's what it does. It's basically bringing the kind of the goal that we have in the beginning together. I can write all these applications using Spring Cloud Stream. I can deploy them. I can register them somewhere. And then I take care of building this pipeline consisting of independent applications talking to messaging systems and deployed on various target platforms. And it supports other, because all this, as you see, creating independent instances, for example, is like all the demo that I did so far was just using one instance of each app. What if I have to create multiple of them? I have launched them separately and so on. I don't want to do that. I just want to go and be able to say, I want 3 of these, and I want them to communicate this way. So this is where the concept of deployment descriptors for Dataflow comes in. Basically, for our example, you can have an application, you can have the worker that does some kind of work count, and then you have other applications like that you need to be scaled out, like something that writes to HDFS. So data, for example, you want to have it partitioned. So that's where basically Spring Cloud Dataflow allows you to provide specific properties for these applications that tell you, I want 2 instances of HTTP. I want 3 instances of work. I want this partition key expression to be used when the HTTP writes data to its output, right? So it's very declarative, very descriptive, very high level in a certain kind of sense. It also provides properties for resource management. So for example, depending on the target platform, you can specify different memory requirements, right? Or CPU if the platform supports that kind of fine tuning. Right? So that's very important, again, for you when you think it, like, it's very important because it gives you a tool to manage your pipeline and to design it without actually having to get into the low-level details low-level details of configuring them at application level. You configure them at the whole pipeline level. So let me just, Andrew, do we have a couple of minutes? 5? OK, perfect. Let me just do what I did with word counts and just do it real quick with data flow and show it exactly what the difference is with what I did before and what I did now. So I'm going to launch the Spring Cloud Dataflow server locally. I'm going to just deploy them on my machine. But first, let me stop all the other running apps. So just going here real quick. I have no applications of my own running. You see I have two apps running here, which are the Dataflow server and the shell. And this is the shell, which is one of the ways for you to communicate with the application. It's basically really a Java command line process. You can just launch it and run. You have other options, like, for example, interacting through web UI. So you can use this to register applications. You can use this to manage streams. In this case, I'm just going to use the shell. So what I'm going to do is I'm going to register 3 applications. One of them is an HTTP source. So as you see, this is an artifact that I haven't developed right now. It's an artifact that we build and register. And actually, we have an entire ecosystem of applications that cover a lot of integrations with different types of middleware. They're all Spring Cloud Stream applications. They're pre-written. They use Spring integration adapters under the scene. So you can just take them, run them, and use them in your application out of the box. Or you can write your own. So I'm going to use 2 of them, the HTTP file and the HTTP source and the file sync. And I'm going to register them. Right? And registration basically gives them a name. It gives them a type, which basically says where in the pipeline they belong. And it gives them a URI, which is a reference to where the artifact lives. And this URI can be a file reference, so you can actually point to a jar if you have access to a shared file system. It can be HTTP. It can be more interesting, like Maven coordinates, if you have a Maven server that you can target. It can be a Docker image if the deployment platform supports Docker. So, for example, when you're deploying Kubernetes. And once you've registered them, a third thing that I'm going to register is the word count application, which I just wrote. So I can just, for example, build this word count application, install it locally, provide its Maven coordinates to Spring Cloud Dataflow. And if you look at, for example, in the UI, if I'm coming back here, you can already see the 3 of them basically register. So you can see what you actually have available. And with this, I can very quickly create a stream. So I can say stream create definition. And the definition is HTTP, which is the HTTP source, pipe word count, pipe file. And let me just give it a port, 9000, and the file has a directory. It's temporary. I'm just going to write this data to a file. And I can also just create and register the stream, or I can deploy it, right? And I can see, for example, how many streams I have deployed, where they are, what they consist of. I can list them, so they're managed entities here, same here, right? You can see it. I can even I can visualize them, for example. I can also visually create these by dragging and dropping boxes into the UI. So while the stream deploys, you can also see 3 more applications coming to birth, right? It just started the file sync, the word count, and the HTTP source. So right now, what I can start doing is just start posting data. Import. And you see the data being basically appended to the file sync. So if I post more data, I will get more data into the. So you can basically see the data being appended to the file sync. And you can see that I actually had a bug in the version that I deployed, because when I testing this before, it actually was counting things and now doesn't count things. So you can trust me that it actually deployed the latest version of the application. In any case, what I wanted to get was, and I'm going to be done, because there are other very interesting speakers coming up, is that you can see you've seen the way to write these applications, and I hope that you get a sense of how data flow comes in and takes these applications and allows to describe complex graphs that consist of them, takes care of their deployment, takes care of their undeployment. So if I do stream undeploy, for example, HTTP file, it will basically kill. On my machine, it means killing the running processes, right? On a platform like Cloud Foundry, it means basically stopping the application. So there are every platform has its own specifics, but the point is that at the end of the operation, you know what you get. Either running applications if you want to start and deploy the stream, or taking them down. In terms of resources, and that's the last slide, it's here. Take some links that will help you with examples that we provide, dive deeper. And obviously, I don't have time for questions, I think, right now, because we need to.
Well, we're up against a break, so we can have questions while people get snacks and refresh themselves.
So I'm happy to answer the questions. I'm happy to talk to over in the open space later on, if that warrants a deeper discussion. So.
Thank you, Marius.
Thank you. Thanks for attending.